My name is Ali Hasnain, and this summer I worked with Dr. Katya Sakara and Dr. Yachi Ji in the Advanced Agents Robotics Technology Lab at the Carnegie Mellon Robotics Institute. My project focused on Blueprint-Augmented Spatial reasoning for embodied agents. Specifically, I explored how architectural floor plans could provide robots with prior knowledge of an environment, allowing them to reason not only about what they can currently see, but also about spaces they haven't directly observed. The motivation for this work comes from a fundamental problem in embodied robotics. A robot can typically only observe a small portion of its environment at any given time. As the robot moves through a building, it collects visual observations like the images shown here. These observations can be used to reconstruct the environment in 3D, but that reconstruction is inherently incomplete. On the left, we may have detailed information about a few rooms the robot has already visited, but the actual building, shown on the right, contains many other rooms, hallways, and connections that the robot hasn't seen yet. This creates an important gap between the environment the robot has observed and the environment it actually needs to reason about. So my project asks, how can we give the robot useful information about that larger environment without requiring it to physically explore every space first, because that takes a lot of time and resources? One framework that provides a starting point for this problem is Spatial, an existing framework out of my lab. Spatial is a spatial reasoning framework that allows an embodied agent to reason over a reconstructed 3D representation of its environment and answer spatial questions. For example, we can ask a question like, which room connects this hallway to the kitchen? Spatial will interpret that question and reason over the 3D scene to produce an answer. The challenge is that this reasoning depends on the underlying representation. If that representation was constructed from only a few observations, then large portions of the environment simply aren't represented. In other words, Spatial can reason very effectively over what it knows, but its knowledge is still largely constrained by what the robot has already observed. That limitation motivated the central idea behind my work this summer. Our idea is to augment the robot's observations with information that may already exist before the robot ever enters the building, an architectural floor plan. The framework starts with two inputs. We have the building floor plan, and we have the visual observations collected by the robot. First, we use a framework called Plan to Scene to convert the 2D floor plan into a structured 3D representation. Even before the robot has explored the entire building, this can give us global information about things like room geometry and connectivity. We can then integrate the robot's visual observations into that representation. The important distinction here is that the two sources provide different kinds of information. The observations provide evidence about what is actually present in the space the robot has seen, while the blueprint provides a structured prior for the rest of the building. The goal is to preserve that global structure while progressively populating the representation with information from the robot's observations. Finally, Plan to Scene Spatial can reason over this augmented 3D scene. Rather than being limited entirely to the observed geometry, the agent now has the potential to answer spatial questions, infer room connectivity, and reason about areas it hasn't directly visited. So fundamentally, we're trying to combine local visual evidence with global architectural knowledge to give the agent a more complete understanding of its environment. There are several next steps or future work directions that we're interested in pursuing next. The most immediate is completing the full pipeline so we can run end-to-end experiments connecting the embodied agent, the plan to scene reconstruction, and Spatial. From there, an important comparison is reasoning using only the agent's immediately observed 3D geometry versus reasoning with the additional floor plan derived structure. This will allow us to better understand when the architectural prior actually improves spatial reasoning. Another direction we're particularly interested in is incorporating generative world models or diffusion models. A blueprint gives us valuable structural information about an unseen room, but it doesn't necessarily tell us everything that may be inside that room. A generative model could potentially combine the blueprint with sparse observations to build a richer hypothesis about unobserved regions. And finally, we'd want to study robustness and generalization across different types of buildings, rather than designing a system that only works for one particular environment. One application where I think this type of reasoning could be very valuable is search and rescue. In a disaster environment, a robot may not be able to safely access every part of the building. Some areas may be blocked, hazardous, or simply too time-consuming to explore, meaning the robot has to operate with limited observations. At the same time, architectural floor plans may already be available to force responders. Those plans can provide prior knowledge about the structure and connectivity of the building, even when the robot hasn't directly observed those areas. And importantly, search and rescue is time critical. We don't necessarily want a robot to completely explore a building before it can begin making useful decisions. So this is a setting where the central idea of this project becomes especially relevant. Can we use prior knowledge of the building to help a robot reason about spaces it cannot yet, or perhaps cannot ever, directly observe? I'd like to thank the Robotics Institute Summer Scholars Program for giving the opportunity to spend this summer conducting research at Carnegie Mellon. In particular, I'd like to thank Rachel Burson and Dr. John Dolan for organizing such an incredible program, as well as my research mentors, Dr. Katya Sakara and Dr. Yachi Ji, for all their mentorship and guidance throughout this project. I'd also like to thank my mentors at Georgia Tech and beyond, and especially Dr. Chuck Thorpe and Dr. Frank Dellert, as well as my family for all their continued support. If you've made it this far, I'd also like to thank you for watching. Thank you.